So basically, the hydrogen atom is the Hamiltonian can be diagonalized once you know the Schrodinger, once you know your spherical harmonics, basically. So it goes like a minus 1 over 2m, and then Laplacian plus the potential, which is ZE squared over R, token acting on psi. And so it turns out that if you put psi equals to R L of little r times YLM, so basically in electromagnetism you learn that this is called separation of variables. But what you see here is really a consequence of spherical symmetry. You can guess that the wave function should be proportional to YLM because this can be guessed because you know that J squared commutes with the Hamiltonian, and so does J3. And that's really, from a linear algebra point of view, that's what you want to first ask, right? What are the observables that commute with the Hamiltonian so that you can use those eigenstates to label to describe your system, the eigenenergy systems. So in any case, what we have discovered is that the differential equation, so this is just a recap, but let's write it down. So you discover that basically the radial wave function can be solved exactly. What you do is you need to make an intelligent guess, and once you have the ansatz, you find that you will be able to get an explicit expression. So give me a second, let me find my notes. There we go. So what you do is you say that R is given by R, you change your variable to rho, R of rho, and it's rho to the L, e to the minus rho, f of rho. Okay, and where rho is given by square root of 2 e bar times r. So if you say my e, I'm going to write it as minus e bar, is where after the bound states. Now the bound states are what's relevant for the energy, the spectral lines that you see, the energy jumps between states. Then if you also define C to be square root of 2 and e over e bar times e squared z, then you discover that rho can in fact, f can be in fact solved. So one thing I didn't say the last time was that there's a recursion relation between, if you set f of rho to a power series, right? So what you do is you say that this is s, start from the zero term to infinity, a s rho to the s, so it's a power series. And what you discover is you can plug this ansatz into the equation, which I won't write down because you can just plug it in. So plug this into E. Then what you discover is you discover a recursion relation that goes like this: is twice of 1 plus S plus L minus C, and then it will be times AS will be equals to 1 plus S, and then it is S plus 2L plus 2, AS plus 1. Okay, in other words, what this is telling you is that if you give me AS, I can get AS plus 1. Okay, and so once you have given me the first coefficient, or rather the zeroth coefficient, basically I can build it up. Okay, I can build up the solution recursively. But what is important here is that you can show. So it turns out that the F actually will go like e to the 2 rho. This is the question I got the last time. If the series does not terminate. Okay. And so in fact, that's why you want it to terminate. So therefore, there must be as maximum, so that F is now sum from 0 to S maximum, right? Not infinity anymore, but the sum maximum. I think I call it S star. You can call it whatever you want. But the point is that you want it to be just a polynomial so that it wouldn't blow up at infinity. Well, the polynomial will blow up at infinity, but it will be suppressed by the exponential, right? And so that's okay. As long as you have an exponential, that's okay. But that's where the condition comes from. The condition comes from demanding that this fellow over here, this fellow over here must in fact be 0, because you want the next term. If this is the maximum, you want the next term to be 0, and the next term to be 0, and the next term to be 0. So if this is the maximum, AS max, then for the next term to be 0, you want this coefficient to be 0. And that's in fact how you get the argument. So I wanted to say this because the last time we were in a bit of a hurry, so I wanted to make sure that at least you get the gist of the argument. Okay, so you want this coefficient to be 0, and therefore that's how you get this expression. Okay, and this is in fact n. Okay, and remember that C is given by square root of 2me over e bar times little e squared z. Okay, so this is n, and what you discover is that because there's L in it, therefore this is how you know that n has to be greater or equals to L plus 1. Because S max is a number, right? A number that goes from 0 to some positive integer. So the minimum this can be is just L plus 1, meaning S can be 0. S max can be 0. But the whole number this entire number must be greater or equals to L plus 1. And therefore, that's how we get this, how we get the discrete bound state energies for the hydrogen atom. This is in fact 2n equals to that. So you can just square it, right? So you get 4n squared equals to 2me over E bar, and then that's E squared Z squared. And so E bar is just given by, is labeled by just one integer n. N is given greater or equal to L plus 1, and that is going to be me over 2 times E squared Z squared. Okay. So divided by n squared, of course. And so the actual energies is negative of this guy. So, so I'm just checking I didn't make a mistake. Yeah, so the actual energy is, of course, the bound state energies. I should emphasize there are also continuum energies, obviously. Those are continuous, but we won't solve for the wave functions then, at least not yet, maybe next semester. We see that the bound state energies themselves are just given by minus E bar n, which means it's just minus, and this is often written in terms of the ball radius. So if you define the ball radius to be given by e squared z to the minus 1. Remember, this is mass, and mass is inverse length, right? So everything else is basically dimensionless in natural units. So 1 over mass is length. And so you can write this in terms of minus 1 over 2me, and then this is actually n times ball radius squared. Okay? And I think we wrote this down the last time already. This is minus 13.6 eV. That's what I always remember. Because that's n equals to 1. Right, so little n is equals to 1 is 13.6 eV if z is 1, and so it will be multiplied by z squared over n squared. Okay. It's good to know some numbers sometimes, just so that you know what the scale of things are. For example, nuclear energies are of the order of MeV-ish. So how do I remember that? I know that the neutrinos coming in from the sun are roughly of order MeV. During the early universe, when the elements were formed, so you guys know, in the very, very early universe, the universe is very hot, and in the very early stages, there weren't even nucleus, there weren't even protons, there weren't even neutrons. So it's only after maybe a minute after the Big Bang, then the nucleus started to form. And that is also around a temperature of roughly an MeV. So you have to remember that's the, even though the protons and neutrons themselves are their mass is around a GeV, the energy levels, the energies related to their reactions and their energy levels are around the order of MeV. And then atomic levels are of the order tens of eV, right? So, of course, obviously, the bigger your Z, the bigger the energies are. But that's at least the idea you should have in your mind. Tens, maybe 100 eV, at most. So to get up to MeV-ish, you need to go to a million, right? MeV is a million eV. So that's quite a few, or many orders of magnitude higher, right? And the reason is of course, is related to the fact that the forces are different. The forces involved in nuclear decay, nuclear reactions are the weak interactions. And also, the next level down is what holds the nucleus together is yet a different force. So that's why the distances are different, right? So the mass scales are different, the distances are different, the energy levels are different. It's good to keep in mind so that you have a sense of what the scales of the problem are, depending on what kind of systems you're dealing with. We will talk briefly about nuclear physics the next semester, very briefly. So what we'll see is that this is the beginning of understanding the orbital structure of atoms, right? So we'll try to understand. So we're beginning to understand how to calculate the energy levels. And so now you have a ballpark. Even more complicated atoms will go something like that. And then we'll understand how understanding angular momentum helps you understand together with the Pauli exclusion principle, how does that help you understand more complicated structure of atoms? It turns out that that structure would help you to understand at least the low-lying nuclear bound states, right? So again, it comes down to understanding the Pauli exclusion principle and angular momentum, but now applied to the bound state of nucleons.
Excuse me.
Yes.
I think this bound state energy come from the assumption that your electron is orbiting in the perfect sphere. So if the orbit of the electron in a perfect sphere, is there any correction for that?
Yeah. So that will be. So we'll talk a bit more next. That's a good question. So we'll talk a bit more next semester. But roughly speaking, your innermost electron will experience a potential like that. Right? This is for the innermost electrons, because you are closest to that nucleus, and there aren't any electrons between you and the nucleus, right? As we know, what happens is that because of the Pauli exclusion principle, you cannot have more than one electron in the same state. So once you have once you have the lowest lying one, the next one must be a bit higher and higher and higher. So as you get higher and higher, it means that the wave function will be localized away, further and further away from the nucleus. And then what will happen is there will be an intermediate, for complicated atoms, there will be an intermediate layer of electrons where they will experience a more complicated potential. But for first approximation, usually you still assume that it has some it's only radially dependent, there's no angular dependence. So obviously it's not an exact statement, right, as I think you correctly point out. But you can think of it as basically the electrons themselves, we're doing quantum mechanics, right? So they're all smeared out all over the place. It's not, you're not looking at real point particles anymore. You're talking about wave functions. So I guess if you average out the potential generated by everybody, to a first approximation, you still say that it is a radial potential. But it is true that it's no longer 1 over r, right? So the potential that the intermediate electrons experience is no longer 1 over r. So that part is more complicated. That's why eventually you have to put it on a computer and try to solve it. But then once you get to the outermost valence electrons, then it becomes simple again, right? Because now everybody is, inside, and you are the only one outside, or maybe there's another one, only a few outside. So then, what will happen is that basically, you see a 1 over r potential, because everybody is everybody is shielding the nucleus, almost shielding it completely, except yourself, right? So if you are only, let's say you are the only one left, you are the only valence electron, depending on, that's the structure of the periodic table, in fact. How many valence electrons tell you a lot about how reactive the element is? Let's say you have one, just for simplicity. Then you will just see basically E squared over R once again, because everybody is shielded except yourself, and the net charge inside is just again 1. You see what I'm saying? And then you'll come back to this again. Yeah. So you go from Z E squared over R to E squared over R, but in between, you're right that it gets more complicated. But because we are still going to make the assumption that it's spherically symmetric, you can still say quite a few general things about the structure, the atomic structure. Yeah.
So I have one more question.
Yeah.
So in case that we can come up with the right potential function for to describe it, so what should be the better way? So should we input the potential function here and solve for
that's right. Yeah.
For this one, or we can use this result and adding a correction.
Yeah. So it depends. It depends, of course. So that's also a good question. So it depends on the situation. So next semester, in fact, we'll start doing some perturbation theory. And what you're asking is exactly why perturbation theory is so important, which is that in situations where you can treat the problem as a perturbation of this problem, then there are tools that you can use to first estimate what is the correction. That's usually how we physicists do it, right? Because we're not mathematicians, so we don't need to be super rigorous. We use a combination of physical understanding together with these kind of perturbation techniques. You can calculate using perturbation theory. And as long as the answer that it gives you is not a huge deviation from the baseline, from the ground, from the exact answer that you start with, then you are relatively confident that you're not too far away. And obviously, as physicists, we also do experiments, right? So you can go out and measure it, and you see, is it in line with what you calculated from perturbation theory?
Correct.
Yeah. So there are perturbative techniques. So for example, next semester, last semester, I made my students do a couple of such calculations. I think one was for the helium atom, which is just a little bit more complicated than this, right? And then we try to estimate, or rather I try to get them to estimate how good approximation is it, right? So you get this, so you next semester with me, probably I'll give the same problem again. So yeah, hopefully you can join us. But those are good questions, right? That's why it takes a while to build up all this machinery. Yeah, very good. So this is just the beginning, but this is also a good place to say, right? Whenever you can solve something exactly, even if it's a toy problem, is very useful because it gives you some ballpark of what the answer should look like, right? So even though this is a hydrogen atom and we don't even have spin, right? So it's not even completely realistic, even for hydrogen. But and then we have relativistic corrections and so on. So all those things will be added later on as part of perturbation theory, and you can see. But the fact that we can have an exact solution for the spinless hydrogen atom is very important. Okay, so what I do want to write down also is the precise wave functions. So what it turns out is that, as you've seen, these states are only dependent on n. So this is why it turns out that R only depends on F. Sorry, F only depends on E only depends on N, right? But F and R will depend in general on L and N. So let me write it. Let me just write it over here, and I'll tell you what the F looks like. So the power law in front and the exponential is fixed, but F, as we've discovered, needs to be a polynomial. We need to terminate the series so that we get a well-defined wave function. So here we go. So in general, F turns out to be something called the Laguerre Polynomials. So let me write it down. FLN turns out to be L of n minus L plus 1, and then 2L plus 1, and then this is a function of 2 rho. So these are called the generalized Laguerre polynomial. And so I wrote down a few for the ground state up to the 1, 2, the second excited state. Okay, so you guys can look it up if you want. But these days, if you have things like MATLAB or Mathematica or Maple, I'm pretty sure they have all of these built in. So essentially, what you discover is that these hydrogen wave functions, they will damp out exponentially at large distances, but at small or intermediate distances, then you get a power law times a degree. This is a degree S max, right? So it is a degree n, 2n polynomial, in fact. Sorry, n minus L plus 1 polynomial. So let me just do that. N minus L plus 1 polynomial. Right, remember that we cut it off at S max. And what is S max is given by this fellow over here, which we call n. So that's why S max is n minus L plus 1. Okay, and n, remember, goes from 1 to and so on. Okay, so that's the start to our discussion of atomic energy levels. But I'm going to move on and talk about the harmonic oscillator first, because there's quite a bit more discussion of angular momentum that we need to have before we can talk more about atomic energy levels. Okay, so we have to be a little bit patient. We're going to talk about angular momentum, addition of angular momentum, and all that fun stuff. So for now, I'd like to actually switch gears a little bit and talk about the harmonic oscillator. This is another simple example that also shows up all over the place in physics. Right? So this is for atomic physics. The harmonic oscillator turns out to be applicable even in quantum field theory. So this is something that appears very simple, but actually is very important. So let's start with the one-dimensional case. And the one-dimensional case is just the case where, again, the Hamiltonian is the sum of potential and kinetic energies. For us, we're always going to be doing p squared over 2m for non-relativistic kinetic energy. But for now, I'm going to set m to 1. Okay. There's a reason for this. Part of the reason is because this will only let us instead truncate it, see how we can do here, and then maybe add the higher order terms as a perturbation. Okay, so this is something that you might encounter in your physics research. In fact, it shows up even in quantum field theory. The more complicated version of this shows up even in quantum field theory, having to add a 5-4 term to the potential. So with that motivation, let's see how do we deal with this guy. So in this case, there is in fact a trick that we can use that appeals to the kind of algebraic analysis that we did for angular momentum. This is also why I want to do this, just to get you guys familiar with it. So, namely, we now have to define these Laguerre operators. Okay, and so what do they look like? I'm going to define them to be 1 over square root of 2 omega, and then momentum operator minus I omega position operator. Okay, and so immediately this tells you that A dagger must be 1 over square root 2 omega, and then P plus I omega x. Okay, so this definition, I hope it's clear, is invertible, right? In the sense that if I give you A and A dagger in terms of P and X, I can now easily invert them and solve P and X in terms of A and A dagger. But I don't need to do it for the Hamiltonian. What I discover is that if I work out A dagger A, let's see what I get here. I get 1 over 2 omega, and then I get P plus I omega x times P minus I omega x. Okay, and what do I get? I get 1 over 2 omega, I get P squared, and then I get minus omega, actually plus omega squared x squared. And then the cross terms, right? So I get P minus I omega px, and then plus I omega xp. So that's basically P commutator with x. Okay, but P commutator with x, we know what that is. That's actually minus, I. So 1 over 2 omega, and then P squared plus omega squared, x squared, and then this is minus I, so it becomes minus omega. And so what we discover is that this actually looks very much like the Hamiltonian, and in fact what we discover is that all I have to do is I just have to multiply both sides by omega and add a half. Right? So H, as you can see, is in fact just omega times A dagger A plus 1/2. Okay, what's the significance of writing H in terms of that? So it turns out, first I need some space. It turns out that A dagger A actually tells you something about which energy state your harmonic oscillator is in. It's called the number operator because it counts which state it is in. So let's try to justify this name. Okay, so what we will first calculate actually is what is the commutation relation between A and A dagger. So let's try that. Okay, so A dagger A, I can pull out the 1/2 omega, and then A is given by P minus I omega x commuted with P plus I omega x. Okay, and what this gives me is that, remember that the commutator is linear. I think is even a homework problem of you, that you guys have solved before. So it's linear, and so I can just work it out. So P commute with P is 0, X commute with P, X is 0. So only Px and Xp needs to be computed, right? So what I have is I omega, and then P commuted with X, and then minus I omega, X commuted with P. Okay, so in fact this is negative of each other, so this is in fact just twice of minus I omega over 2 omega, and then xp, and then xp is I, so that just gives me I times minus I is 1, and so I get 1. So in other words, A dagger commutator is 1. Now let's consider what happens when I commute N with A. Let's do it with A first, okay? What you have here is you get A dagger A commuted with A, and again I think it's your homework problem. You realize that if you have A, B, C, you first have A dagger A commuted with A, which is of course 0, plus A, C, B. You get A dagger A, okay? And so this is 0 for sure. A dagger A, we just showed that A dagger is 1. So A dagger A must be minus 1. So N commuted with A actually returns A, but with a minus sign. Okay? This should remind you of the raising and lowering operator that we got. So maybe I'll recall commutation relations between J3 and J plus minus. Okay, so you guys should look back at your notes, and this is like J3 with J minus essentially. Okay, and then now what we're going to ask is N A dagger. Okay, so N, it turns out to be permission, right? So N dagger is just the dagger of A dagger A, which of course is just A dagger A. So N is permission, whereas A is not. But what I can do is to get, here I don't have to calculate again, I just take the dagger on both sides of this relation. And what you can remember is that if you take a dagger of A commuted with B, you get negative of the commutator of A dagger with B dagger. So when you take the dagger of that, you get minus N A dagger equals to minus A dagger, which means that N commuted with A dagger is in fact plus A dagger. Okay. Again, this one is like J3 commuted with J plus, if you look back at your notes. Okay. And so at this point, and so let's consider the following. Suppose N applied to some cat gives you some number times cat. So it's an eigenvector. Okay, so now let's consider a dagger applied to this guy, and then we apply n to it. So what is that? So I can now commute through. So I get n commuted with a dagger, and then I need to cancel out the second term. So I add a dagger n, and then it's applied to little n. Okay. Right. So this guy will cancel out the second term, negative a dagger n. And now we know what this is. This is just a dagger, and this is plus a dagger, but multiplied by little n, acting on n cap. So this is actually n plus 1 times of a dagger n. So what does that mean? It means that if I apply a dagger on n, this turns out to be also an eigenvector of n if this guy is already an eigenvector. But now it's not the same eigenvalue, but the eigenvalue plus 1. Okay, very similar to what we did for j plus minus and j3. Right? In other words, a dagger is the raising operator. Very similar to what happened for j plus. Okay, and likewise, if we do it for a instead of a dagger, then we can play the same trick. Right? So this is n commuted with a plus a n. This is now little n. This one is now minus a. So therefore, this is actually n minus 1 times of a n. Okay, so again, if n is an eigenvector of capital N, then a n is now an eigenvector of n as well, but with eigenvalue 1 less than 1 less. So what does that mean? It means that we can now build things up, just like we were able to do for the eigenstates of J3. We first have to argue that it's either a maximum or a minimum, right? That's what we did with angular momentum. In this case, we're going to prove that there is a minimum for the eigenstates of the Hamiltonian. Okay, and so how do you do that? So claim there is a minimum. Okay, so how do I know that? So let's think about the following. So where's my notes? So the way to think about it is to calculate the expectation value of the following. We want to find out what's the lowest energy level. Okay, so if E, in fact, is an eigenstate of H, then we can consider the following: E, H, E. Okay, well, this is the eigenstate, so it's just E. So, but we can also write down that this is omega A dagger A plus 1/2 E. So this guy in particular can be written as omega, and then it's the norm of A applied to E, dagger applied to A, E. Right, so this is the norm of some state plus 1/2. Okay, so this is just a norm. This is the norm of A, E. So whatever this energy is, you can see that this has to be greater or equals to omega over 2. Why? Because the norm, again, is a fundamental assumption of linear algebra, right? That this state, the length of the state, the square of the length of the state, cannot be negative. So because it cannot be negative, the energy can be any energy you want, has to be greater or equals to omega over 2. But if the energy cannot be greater or equals to less than 1 omega over 2, and the energy differs only by 1/2 from A dagger A, therefore N also has to be bounded, right? So because N commutes with H, they share the same eigenstates. So we can see that N, the eigenstate of N has to be bounded as well.
Excuse me.
Yes.
It's just a little bit confused.
Yeah.
So in omega over 2, the correct way to write it is omega over 2 plus multiplied by some constant, because you have the energy is in energy. Yes, you have the energy, but you have omega over 2,
yeah.
Omega in the angles. So you say something that energy like greater than the angle is not in the
omega
same scale.
is just the frequency.
Yes, the frequency.
Yeah.
So
which is the energy, right? Actually it will turn out that omega over 2 is the ground state.
I mean that if you want to compare between them, should you exactly the correct way, the exact way you multiply by some constant to make it come to the energy scale.
Oh, you're wondering about the dimensions.
Yes.
Is that what you're, because you remember I set my H bar to 1.
Yes, that's what.
And then I also set my M to 1. So that's why everything is dimensionless now.
Yes, so that's what
So
I
the
asked.
only scale, hang on. So the only scale is omega here. Yeah. So if you want to put back the energies, I think there is some M's, I think, but let's not do it. Okay? Let's not worry about it because it's not. I've got to think about it a little bit, but we can put it back. But this is a correct statement because of this.
I know that for theory go, guys, we like to do it like this to simplify the problem. For me, it's parentless. When I look at this, I need a constant to multiply so that I can solve it. Possible.
So in fact, I would say the other way around. It's better to get used to this because it's very useful for solving problems in such a way.
I mean, so when you come to the solution, you need to put it back to
even then, you don't really need to know if this is your only. If this is your only scale of the problem, you can use mass. You can use your mass, as the fundamental unit of energy. So don't worry about that. So in fact, let me say this, and then I'll let you guys take a break. Give me 1 second. Let me erase this part, and then I'll explain what I mean. Okay, so let's say mass, let's say you know in this problem that your mass is, say 1 kg, okay? So we know that this has to turn out to be energy, right? So if you set actually I like to set everything to 1, so my H bar is 1, my C is 1. So I claim that 1 kg is also energy, right? Because C is 1.
Yes.
So therefore mc squared is just m. And so this is in fact energy. Okay, so you can use this unit, 1 kg, as your base unit for energy. So whatever this number turns out to be, it will have to be a multiple of 1 kg. Because you know that that is in fact energy. Right? We're calculating energy. So the key point is to know what you're calculating. So omega over 2 is also energy. So the only dimensions you are leaving out is the fact that this is units of energy. Right? So let's say I do a calculation, I found that omega over 2 was 1.23. Okay? And what does that mean, right? That's your problem. You're asking, what does that mean? I mean, there's no dimensions here, and the professor is a bit cuckoo, right? So no, the professor is not cuckoo because m, you know, is 1 kg. So this, in fact, if you believe that this is the units of energy, it's just 1 kg. Yeah, 1.23 kg. Yeah. So for example, that's also why you often see particle physicists will tell you that the mass of the electron, what is the mass of the electron? 0.511 keV. So 511 keV, right?
Yep.
Yeah. So how can this make sense? This is actually electron volts, right? Again, electron volts is the you would think of it as, you know, if you take an E&M class, is the amount of energy to bring across an electron across 1 volt, something like that, right? But it's not mass. But again, because C is 1, right? So if I want to put back my mass, I can, right? Because I know that this is this has to give me energy. If this is energy, then I want to put back my C, so to speak. Then I know that, well, energy is mc squared is energy, right? So therefore, if this is actually mass, if I want to put mass back, then all I have to do is I just have to remember this relationship and divide by c squared. So therefore, mass is just of electron is just 511 keV divided by c squared. Right. So you just have to know what is it you're calculating. That's number one. And then number two, of course, you have to remember what is actually C and H bar. Right? H bar is energy times time. C is speed. Right? And so depending on which way you want to go, if you're willing to stick with 1 kg as your energy unit, that's actually completely fine. But if you insist you want to get from energy back to mass, then you have to put back 1 over c squared. For example, if you talk to your high energy physics friends, people who actually measure things like the particles coming out of the collider, and you look at the code, I claim they do the same thing. You will not see a C in their code, because you know who cares? The C is just a number that you just carry around, right? You know, why carry this number around everywhere in your code when it's the same number, right? Who cares? So just drop it, because you know it's the same standard, right? Everybody knows what is C. You won't ever go to NTU and you discover C is a different number in NTU than in NCU, right? That would be bizarre. Yeah, so I claim, if you talk to your friends in high energy physics, they will in fact tell you the electron mass is 511 keV. They put that in the code.
Can I ask one more question?
Yep.
Extra question.
Yeah.
I'm medical physicist, by the way, and for all of my divine energy calibration, we use 511 as a base. So we define 511 keV plus minus 0 to be the base for our energy calibration. I was just wondering how people define the electron mass is 511 keV precisely. So all the physics are both built on it.
Yeah. So that's a good question. So what you're alluding to is not quantum mechanics per se, right? But
Yes.
it's actually a physics question, which is that I think there's even a word for this, meteorology, I think it's called. But it's about how do you define the fundamental constants in nature. So in some sense, to me, it's a very interesting question because it reflects our own understanding of nature. So why do I say that? For example, we used to measure 1 meter, right? I don't know about the answer for energy, unfortunately, but I know the answer for length. So I'll give you that example. But this is an issue, right? How do you define the fundamental constants? How do you measure length? How do you measure time, and so on, right? So length and time I know very well because it has to do with fundamental physics. So length is defined, used to be, you can go to Paris and you find this block of something, and then, that's the definition of 1 meter, right? And then in the old days, it's like some king, and then you measure the elbow to the finger and so on, right? It's obviously not going to be very accurate. What if the king is malnourished and he starts shrinking, or let's say he gets sick, right? Or someone chop off his hand. Now what happens to your 1 meter, right? So you obviously want to use something very fundamental, something about the nature of the world itself, right, to define 1 meter. So nowadays 1 meter is defined. What is it? Is 1 meter is the distance traveled by light in vacuum in 1/299792458 of a second. That's how it's defined. Why? Because we can actually measure light, time very, very accurately. How do we do that? That's quantum mechanics. You make use of the oscillation, the cesium atom, and we believe that we understand how quantum mechanics works, right? So we believe the cesium atom oscillates in a very well-defined way, and somehow we can measure that. The details I don't know, but we can use it as a measurement of time very, very accurately. So because of that, we can turn it around, and because we know light, we believe light is such a fundamental aspect of nature, we use its speed. Right? Otherwise, special relativity wouldn't be around. Right? It's such a fundamental unit for speed. We use it to measure distance. That's one example. Yeah. So there are other examples involving, for example, electric charge and so on. Right? But again, I think more and more, I think recently there was one about H bar. I forgot now, there's even a news story about this. But again, more and more we're moving towards a place where we define the fundamental constants based on our understanding of the physics underlying the world. Right? So we use benchmarks that are not arbitrary, right? Not some king or some president's arm or whatever, right? That's ridiculous. But actually based on the real world, something very fundamental about the world that wouldn't change. Yeah. Okay, let's take a 10-minute break and then we'll come back. It's now 05. We'll come back at 15. So, we're talking about the eigenvalues of n and h. in fact, what you can see is that basically the two are related. So H acting on, for example, H acting on N, what is that equal to? That's in fact omega N plus 1/2 of N. So E is in fact omega times N plus 1/2, which just means that if I can diagonalize N, the eigenvalue of capital N, which is little n, if I can diagonalize that basically diagonalizes H. Right? And so what in fact we have shown is that this guy is greater or equals to omega over 2, which means in fact that N is greater or equals to N plus 1/2 is greater or equals to 1/2, which means N is greater or equals to 0. Okay. In fact, that's what we're going to discover. We'll discover that N is in fact, the lowest N is 0, and then there's 1, 2, 3, and so on. Right? But we have to prove that. So, how do we prove that? Well, what we've discovered is that there must be a minimum, right? So let N minimum be the state where A acting on N minimum must give you 0. Okay. How do I know that has to be true? Because if it were not true, I can keep going lower and lower and lower, and I will find that it will violate this bound, right? Because if it were not true, then N would not be greater or equal to 0. I can keep going lower and lower, I'll be able to violate this eventually. So it has to be true that if I keep lowering and lowering, at some point, I will be able to get 0. Yeah. So what is that? So that we can use to, in fact, determine, just like we did for the raising and lowering operator case for J3. Remember that we use this argument to argue that J3 has both a maximum and a minimum eigenvalue, right? Because the bound in that case is a little bit different from here. But now that this is true, we can in fact right away figure out the energy level. This is in fact nothing but H applied by N minimum is in fact, well, let's start with N in fact. So if this is true for A, that means that A dagger A, because A is applied to this, is in fact 0. So N is in fact nothing but 0. N minimum is nothing but 0, as we have claimed, right? Because again, there has to be a state where once we lower it one more time, we get 0. But that means A dagger A acting on it is 0, which means little n is 0. But once we know that, then we know that applying it, the A dagger, so this is the minimum. So if I apply A dagger n times to 0, then that would in fact give me something that is some constant, which will determine in a little bit, times the nth eigenstate. So in fact, this is why we know n is 0, 1, 2, 3, and so on. Okay. So all the symbols remain the same, except now we realize the energy is labeled by n, where n is in fact an integer. And that's the simple harmonic oscillator energy levels. So the interesting thing to note is that, remember that the potential is a parabola. That, for example, the ground state wave function. Right? So this is just to emphasize to you that if you have these methods available to you, you should use them because it's much easier and you get more insight into your dynamics if you have these properties than usually a brute force solution would give you. So let's try to do that. Okay, so how do we do that? So if you remember, we got the spherical, the highest. If you because I erased it, let me just write it down here. Recall, we could derive YLL or and YL minus L, the spherical harmonic with the highest n value by demanding that J plus of LL in the position space was 0, right? Because this gave us a differential equation, a simple differential equation that we can solve. And likewise, when we lower L minus L, this was also 0, and you write it down in position space, that also gave you a differential equation that you can solve. So what we're going to do is we're going to do the same thing, but now for the harmonic oscillator, and see that we also get a simple differential equation. So now we do A acting on 0. So we figured out that the lowest eigenstate is 0. And this is 0. But now let's try to do this in position space. Okay? But we know what this is. So this is 1 over root 2 omega x. And then P is a sign that I always don't remember. P minus I omega x. Okay. And so P we now know very well is just, so is 0, so I don't need the 1 over root 2 omega. But P I need is minus I dx, and then minus I omega x. Whole thing applied to the ground state wave function of the harmonic oscillator. Okay. And so what this is saying is that I can now write down a first order differential equation, right? So what does this look like? Let's write it down. So this is dx. I can cancel out the minus sign, and then I can also cancel out the I. So it's x 0, and then I can move this down on the right hand side. I get minus omega x, x 0. Okay. And then now I can just divide by both sides by the same wave function. So I get basically f dx log of x 0 equals to minus omega x. Okay. And so I can just integrate, right? So when I integrate it, I get log of x 0 equals to minus omega over 2 x squared plus a constant. Okay? And now I exponentiate it. So I get x 0 is the exponential let's do it, e to the minus omega over 2x squared plus a constant. But e to a constant is just another constant, right? So let me just write it down as c prime, so just another constant, e to the minus I omega over 2x squared. So how do I fix the constant? Just make sure that this guy is normalized to 1, right? So I just have to make sure that when I integrate from minus infinity to infinity, the square of this guy, which means e to the c squared, let it be real. There is a choice of phase, so let me just let it be real. C times squared times the integral of the Gaussian. Must in fact give me 1. Okay. Do you guys all know how to do the Gaussian integral? Yes? Yeah? Who doesn't know how to do the Gaussian integral? Yeah? Okay, so I'm just going to write down the answer, okay, so everybody knows how to do it. So in fact, what you find is that C is just omega over pi to the 1/4 power, and therefore x 0 is in fact given by the 4th root of omega over pi to the minus omega over 2x squared. Okay. And now we have the ground state. So in fact, you can use this technique to get all the excited states, right? Because you know that x a dagger to the nth power acting on 0 should give you something that is proportional to x pn, or the nth eigenstate. Okay, I say proportional to because the main problem is how to normalize it properly. Okay, and that is the main issue that we need to tackle. But otherwise, let's write it down. This is what? This is x, and then a dagger is just p plus I omega over square root 2 omega. Apply n times on the ground state. So this in turn is just nothing but minus I dx plus, oops, I'm sorry, there's an x here, plus I omega x over square root 2 omega. The whole thing apply n times to the Gaussian e to the minus omega over 2 x squared divided by 4th root of pi over omega. Okay. Like I said, it's not normalized yet. Okay, so we're going to figure out how do we actually normalize it. That's the problem. So let's try to figure that one out. So there's a trick here. The trick is the following. So we need to figure out the proper normalization. It will turn out to be a factorial, but it's not completely obvious yet, so let me just write it down. So we need to do the following, which this will give us zero, a, we need to normalize this state. Okay? So what will turn out is that we want to normalize a dagger, a to the n, a dagger to the n, 0. Okay? Because this is proportional, this is the normalization of this guy, and once you have figured out the normalization of this guy, you can then divide by the square root of the norm, or divide by the norm. Okay. So what you see is that you need to figure out what is A dagger n, and try to figure out how to use that to properly calculate the normalization in this guy. So this is a trick that shows up even in quantum field theory, which is the following. You know that A applied to 0 will give you 0. A applied to 0 on the left will not give you 0. That's why you get the excited state. So the trick is to figure out how to move some of these guys over here. Okay? And so in particular, what you're going to write this as, this is A dagger n minus 1 acting on 0 dagger. So this is the nth minus 1 state. But now, the extra A here, you associate it with this guy here, A dagger n. Okay, and if I can find a way to commute through, then we'll see a pattern. Okay, and so the point here is that, so the claim is the following, that you can commute A with A dagger n in the following way. It turns out that A commuted with A dagger n is in fact n times A dagger n minus 1. Okay, so let's see that it is useful before we continue. So why is it useful? Because if I can do that, then A dagger n acting on 0 can be now written as A commuted with A dagger n, and then I need to cancel the second term, which is A dagger n A acting on 0. So if I know how to calculate this, then I have successfully managed to move A to the right. And A acting on this guy is automatically 0. Okay, and so this will give me, if this is correct, this is n times A dagger n minus 1, 0. Which means that the normalization of this guy is related to the normalization of the n minus 1 case, right? So A dagger n minus 1, oops, I'm sorry, n, we have discovered is in fact equals to n times A n minus 1, A dagger n minus 1. So now there's a recursion relation. The nth case is related to the nth minus 1 case times n. So we can keep going, right? So clearly this will be n times n minus 1, 0, A n minus 2, A dagger n minus 2, 0. So all the way down to, you can keep recursing until you get nothing, until you get to the nth case, n minus 1, n minus. So this will in fact be equal to n factorial 0, 0. And that's how you figure out this normalization. So this is 1. So basically, you want to say that A dagger acting n times on 0, you want to divide by the square root of n factorial, and you want to call that your nth excited state, the normalized n excited state. Because then when you take the norm of this guy, you get 1, right? Because the norm of the numerator we've just discovered is n factorial, and then you divide it by the square of the denominator, that will give you 1. Okay, so this is this is the punchline, that just from the algebraic properties of A and A dagger, you can figure out the normalization. And so the only thing we have not shown is how to verify that claim. And usually what you do is when you have a claim that depends on some number n, the first thing that you might want to think about is to prove it by induction. Okay, and so let's try that. Any questions so far? Yes, I'll make that, I'll prove that claim by induction. So, you start with the most basic claim, right, which is n equals to 1. So, when n equals to 1, we already know the answer. A dagger is just 1, as we have proved already. And that is, in fact, 1 times A dagger, and then add 1 minus 1. That's exactly what the claim means. So then we suppose that the case is correct. Then let's consider A commuted with A dagger K plus 1. Okay, and so this is now A dagger K, right? And so this is, again, where you, if you remember the property that you proved in your homework, this is in fact given by A dagger K, of course that's 0, plus A dagger K. Okay. Yeah. ABC is ABC plus BAC. Okay. And of course this is 0, and that one we have just shown. We have just assumed that the case is true. So this is A dagger times the case is K times A dagger to the K. Okay, K minus 1, I'm sorry. And so therefore, this and this will give you K. Oops, did I mess up? K, yeah, that's right. K times A minus 1, K. So this should be K plus 1, right? Oh, sorry, this is A dagger, my bad. So that is I made a mistake, right? So this is A dagger to the K. So this is in fact 1 times A dagger K plus this guy. So this is in fact K plus 1. So if the case is true, which means A dagger K is K times A dagger K plus 1, K minus 1, then you expect you can just shift your K by 1. So K plus 1 will be K plus 1, K goes to K plus 1, K minus 1 will go to K. Right? So therefore, the K plus 1 case is true. And since the n equals to 1 case is true, that means the n equals to 2 case is true, n equals to 3 case is true, and so on. Right? So you've proven the claim for all k. And that's what induction means. When you start from 1, you assume the k case is true, and you prove that the k plus 1 case must be true, and therefore the whole thing is true. Yeah. So to summarize, what we have done is we have just used the algebraic properties of the ladder operators to get the ground state energy, and from that you just keep raising to get all the energies. But not only the energies, you can also use the lowering operator acting on the ground state and use that relation, convert that into a differential equation to solve for the ground state wave function, which is exactly this Gaussian that you see over here. And from that, once you have the Gaussian wave function for the ground state, you can again use the raising operator and get all the excited states, which is this operator acting n times on the Gaussian. That will give you the nth excited state. Okay. So the harmonic oscillator can be solved completely using this kind of algebraic methods. Okay. But of course, this is one representation, and so in your homework, you will in fact discover that there are other there's the kind of brute force way to do it, right? Which is to simply solve the differential equation for the wave function. And what you discover is that the wave function will be a Gaussian times what is called a Hermite polynomial. So what you are helped by, what you are aided by is that you know that your wave function, you see these guys will just be derivatives of the Gaussian time plus some x, right? And then you act it multiple times, so you will always have, so let me just write that down. So wave function, energy wave functions by ODE. Right, so if you solve the Schrodinger equation directly, then what you can say is that psi must be e to the minus omega over 2x squared times some function which I call Q, in my notes I call QL of x. Okay? In fact, I call it C. Where C is square root of omega times x. Okay, and so what you will discover in your homework is that when you plug it in, when you plug it into this, so you get minus 1/2, n is 1, remember here, so dx squared, and then plus potential energy acting on psi equals to E, and E you know is omega times n plus 1/2 of psi. Okay, what you discover is that Qn will obey the following equation. Qn double prime plus 2c Qn prime plus 2n Qn equals to 0. Okay? And this will turn out to be the Hermite polynomials. Again, I'll let you guys figure this out for your homework. Okay? Of course, it's a second order ODE, So there will be a second solution. But I believe what you'll discover again is that the other solution will not work because it doesn't, you cannot normalize it. You cannot normalize it properly. Right? It's usually like that in quantum mechanics problems. Well, I'll let you guys, this is homework. You guys will figure this out for homework. And we'll give you a chance also to get familiar with some special functions. Any questions for me? No? Okay. See you guys on Thursday.